So what we'd like to do is take a look at the B and H fields in a little bit more detail and look at boundary conditions of these vectors at interfaces. So what we're trying to do is determine a little bit more about the nature and the relationships between B and H, and of course we'll try to determine the boundary conditions. Let's look again at the derivation of H, and recall it's going to be a quantity which depends on B and capital M. So let's suppose we have the magnetization M material such that M is unequal to 0, and there are bound currents, so we'll take the bound current only, the bulk current density, and that's the curl of M. If there are free currents either surrounding or inside the material, then we'll take the total current as being the sum of the free current density and the bound current density. B depends on both of these, and so we lump them together into J, the vector J. If we look at the curl of B, then it will be related to the total J by the curl of B equaling mu 0 J. Remember, this is Ampere's law in differential form because we can start here and get our loop equation. Taking the mu 0 on this side, we end up with this equation here where we've substituted in the definition of the bound current density. We collect the curls, so we have curl of this quantity here, and that's equal to the free current density. We define the quantity, which is the summation of 1 over mu 0 B minus M as H. So I've just repeated that here. Here's the definition of the H vector. So that's what it says here. If we start then with the curl of H right here, then we can change that into the line integral of H around a closed loop C, and that will be equal to the free current enclosed. That comes about by the fact that this is J sub F, so when we form this integral, we'll be taking a surface integral over J sub F, and that gives us our I free enclosed. The quickie version of that then is you start here with the curl of H, doing the surface integral of this quantity over that surface, changing the curl of H into J sub F. We now have a surface integral of this quantity here, and that's going to be basically looking at the right hand side, which is right here, and this is the left hand side here. The right hand side can be transformed into a line integral, so we have the line integral around a path around the surface S. So this quantity here will be integrated over the path. The right hand side, as you can see, is a current that will be passing through the surface S, and we call that I free enclosed. So remember that this is the free current passing through the loop, and that loop C is bounding the surface S. So remember that this free current is the only current that we control. So in other words, if you have batteries, you have power supplies, you have wires, coils, solenoids, toroids, etc., you combine these together to give you currents in space through these kinds of structures. As a result, because you have, and this is all free current, you can obtain an H which is in many ways easier to measure, and sometimes it's easier to calculate. Looking at the difference between these two, the first thing is we put a lot more emphasis on this field here and consider it fundamental by the fact that it exerts forces on moving charged particles, which is where we started in terms of the behavior of B. H is another field which we derive from B and the magnetization M, and this is convenient to add to our collection. So two differences between B and H are that the curl of H is only dependent upon the free current density, and that the line integral of H about some path C is equal to the free current enclosed. This is compared to the curl of B, which is the total current density, so the sum of the free and the bound charge densities. Well, if you integrate these two like we did the H vector, you end up then with the line integral of B around the path C being the sum of those two currents. The other difference is that del dot H is not always 0. whereas we know that del dot B is always 0 because there are no magnetic monopoles. For example, inside magnetic materials, where M is unequal to 0, then if you write down the divergence of H, which is right here, this is the definition of H, and commute the divergence operator, you still have the divergence of H here, but look, you've got the divergence of B, which is equal to 0, minus this quantity here. Well, that equals this divergence, and is often non-zero, so we have a divergence of H perhaps, and it's common that it's unknown. Now if you remember the Helmholtz theorem, it says unless we have both the divergence and curl of a vector, and this includes H, you cannot determine it uniquely. Often this will leave us hanging. All of the above is true even if you have M not proportional to B. So let's suppose we have this situation. We can turn it around and make B proportional to M. And if you remember, this leads to an equation for B in terms of a constant mu, which is the permittivity of the material. All of this statement here will only hold for a linear magnetic material. If we rewrite H for the case where we have this proportionality, here's our B right here, then we can factor out the vector M, and so we would have this quantity here and times M, and you recall that what we've done is taking mu over mu 0 and define the relative permittivity as we did before. Turning this around, we can write M proportional to H, and again write this in terms of a constant, and this is the magnetic susceptibility. If we're given this equation here, we can often solve the problem of external currents given H for B and M, both inside and outside of a magnetic material. For example, when you have this equation here, it can sometimes for certain geometries be solved for H. When is this equation here likely? When do we have this very tight connection between M and H, the linear equation? One very important case would be the diamagnetic materials, another would be paramagnetic materials. And we've discussed that this quantity here is positive for para and negative for dia. So in principle then, with this combination, we can determine both M and B from H, assuming that we can find it from the free current densities. And we've already done this in an example or two beforehand. One fundamental relation is always true, that if you go out into free space where M is equal to 0, you'll have B equaling to mu 0 H. So B outside can always be determined from H outside or vice versa. So where do things get hairy? Well, it's when the relationship between M and H is unknown. You may not have the simple proportionality. And that's the case for the situation where you have ferromagnetic materials that have permanent magnetic magnetizations. And so when you turn off the free current densities, or free current could still have a residual M. And the equations for predicting that may be basically unknown. There's a case then if you don't have any free currents. Well, if you look at this, you don't have any free enclosed currents. So as a result, the integral of H dot dl is equal to 0. You might be tempted to then say that H is equal to 0, but that fact is not true. This does not imply that H equals 0. What it does mean is that the integral of H around the circle is 0, but that does not mean that H is 0. Let's consider the problem of finding B from a uniformly magnetized sphere, which we've done already, and that's a case where you have 0 free current. So the question is, can we find H? Let's review the problem that we solved before, and I'll go through this very quickly. We have the magnetized sphere, we found the surface current density, and we found the bulk current density, which happened to be 0, and this is the surface current density, that is the bound current density. These are currents that are running on the surface of the sphere, and if you remember, they're basically running in this phi direction like this. I won't go through the final result, but what we did is that we used that bound current density to find a magnetic moment due to the magnetized material. that value was right here. The magnetic dipole that is due to that magnetized material is just equal to m times the volume of the sphere z hat. If we leave it in terms of the radius of the sphere, you see here is 4/3 pi r cubed. That led then to finding the field outside first. So we take the B field of the dipole, this dipole right here, it will have the moment that we just determined. Well, if you remember, the field of a dipole away from the dipole itself is a prefactor here that has the dipole moment over r cubed, and then we have a factor that's in the r direction, and we have a factor that's in the theta direction. So substituting in our m, we get this expression here with the same form for the parentheses factor. So that's B out, and it's the field of a dipole. So let's repeat that panel that we just saw, and we'll take the expression here for the B outside, which is going to have two components, the radial component and the tangential component. If we go inside, we want to make some assumptions about B. Because m is a constant, we'll take B inside to be uniform, and we'll take it in the same direction of m, namely the z direction. So we just write down that the B in will be of the form, this equation here, the magnitude and the direction z hat. In order to find this expression right here, the B in, we're going to use a boundary condition that we'll derive in just a little bit. But let's just take it as is. We're going to show that the B normal is continuous at the interface. In this case, it's the vacuum magnetic material interface. Realize that for the sphere then, the n hat vector is just the r hat vector. Those are the normal vectors. If we take this B in normal, that's going to be equal to the B in z hat dotted into the r hat vector. Given that this is what we're after, it's sitting here, and the dot product of these two unit vectors will just be the cosine of theta. B out has to be evaluated at the distance r. It's still a function of theta, and we're interested in the normal component because we're going to say that this will be equal to the normal component inside the sphere. And so that means that we're only going to have the r component in B out. So if we write down the first term at capital R, so here's where we set little r equal to capital R, and then this is times 2 cosine theta r hat. And so up here, this is what we've got so far, and we throw this term away because it's tangential. So we're only left with this expression here. So simplifying that then, the magnitude B out at the surface of the sphere is just equal to this quantity here. So we set that to B in at the interface, and that's given by B in, basically, times cosine theta. If we make that connection then, we solve for B in at the interface. It's equal to a very simple expression here, and because B is uniform, that corresponds to any position in the sphere, and that gives us B inside. So turning it into a vector, we just multiply by the direction of B in, and we have the full expression for B sub in. So if you go back to m, you can see that this B sub in is just equal to 2 mu 0 over 3 times the m vector. I want to remind you that this is a permanent magnet, and m is uniform and non-zero. It therefore generated a B out even with m equals 0 outside, of course. So there's a B field outside even though there's no magnetic material. We also know that there's a B field inside, so that's equal to this quantity, and here's B out again that we wrote down before. So now let's go to H. H is defined as 1 over mu 0 B minus capital M. If we go inside, the H inside will be equal to B in, sitting here for B, and of course M stays here. We know that B in has a form that where it has capital M in it, and that's this term here, so this is 1 over mu 0 times B in, and then here's our minus M right here, minus M z hat. We've got two factors that have the same direction, so we can factor those out. So here's the prefactor times z hat, and you'll notice that if you just take this difference that we have minus 1/3 times capital M times z hat equal to h. Since m is not equal to 0 inside, we have a non-zero h inside. Notice that the minus sign tells us that it points in the opposite direction to both b and to m. Let's get this down here, that outside in free space, here's h out, is 1 over mu 0 b out, and so that gives us then h out that looks like this, and all we've done is taken our b out and divided by 1 over mu 0. Let me repeat. Outside, this is the expression between h and b because m equals 0, and so you get this simple. And as always, this h field is in the same direction as b out as long as we stay outside. To repeat then, this is a permanent magnet, constant m, in the shape of a sphere. That's all we needed to know to find b and h. We got b from m and the bound currents that resulted. We got h from b and m. So here's a sketch of the two fields. Here's the field outside of a dipole. This is the B field outside of a region where it's a dipole field. And it's equivalent to a dipole right here at the center of the sphere in this direction. But we stay outside with the dipole field. Inside we have the uniform B that's in the direction of M. This is the direction of M, and this is the Z direction here. Okay, so you'll notice that the field lines are continuous. There's no change in direction as we go around the loop of each B, and gives us the picture that we have here. You may think that that's obvious, but we had to do actually some logic and some careful equation building to get this expression here. Now look at H. Okay, remember that outside it's just like B except it's 1 over mu 0. And that's what we have here. So we show basically the same streamlines as we have for B. But inside we have the H field pointing in the opposite direction. So this streamline here comes up here, but then it's facing a vector that goes in this direction. Clearly there's a discontinuity in H across this interface. Remember that M is in this direction, H is in this direction, and if we go back and look at the magnitudes, H is minus m over 3, whereas B inside, if I can find it, B inside is 2/3 mu 0 times capital M. You can see the difference between the B field inside and the H field inside. So here's a case then where M is the only source of the field. There are no free currents. H is not 0, and in fact has values inside and out that are different than 0. Let's look at the boundary conditions, and we're going to look at an interface between two materials with different mu's and two different chi's. We're interested in first looking at the normal component of B, the B field. Remember that if we do normal components, the geometry of the pillbox is important. We have then a pillbox with an area up here, or a surface that we call delta S1, and we have one on the bottom which is delta S2. So the scalar values of these two quantities is just basically the area of that surface. If you take the vectors, those are normal to the little surface elements, and so you can see this one is this direction, this one is in this direction, and the height we're going to take is very small. You can see the total height is delta H, and we're going to let that go to 0. The normal vector that we're interested in is the one that points in this direction here, and so it goes from 2 into 1, and so that's the notation we're using here. With this in mind then, here's the pillbox. We're going to let delta H go to 0. We have these two surfaces which are parallel to the interface. That means that the normal vectors representing the areas are perpendicular to the interface, and they'll have, of course, the opposite direction. In order to evaluate this normal change, we're going to use the fact that the surface integral of b dot capital DS, so this is over a surface, is equal to 0. And so what that means is derived from the fact that the divergence of B is 0, is that there are no sources or sinks for B inside the pillbox. In other words, there's no monopoles. We make this small so there's no contributions on the side of the box, and we're going to say that this is so small an area that the B up here and the B down here, they are constant over each of those areas. So we set up our surface integral here, and because B is constant over that surface, we can bring it outside. Because ds is normal to B, this would have originally been just B ds in terms of scalars, and then we bring the B outside. Because this is perpendicular to the interface, this gives us the normal component of B. The first surface we're integrating over is this one up here, and the second one is here. And so if you look at the change in the direction of the unit vector, we'll get this minus sign here. And so here's the total integral, which is given by this, and that's going to be 0 because of the initial equation up here. The way the pillbox works, this area up on top and this area on the bottom are equal to each other. So that means we can just divide by a delta S so that this cancels, and we are left with the normal components of B. So this right here really is the boundary condition that gets us started. It just says that the normal component of B is continuous. For a linear material, we can set B equal to mu h. Here's the vector version of that. On top we have mu1 h1n. On the bottom we have mu2 h2n. So this gives us the boundary condition on the normal component of H. We quite frequently write this in terms of a dot product, and so for B, if you take the normal vector as we talked about here, then what we have is a dot product of B with the unit vector equaling the dot product with the unit vector, where this is in 2 and this is in 1. Together with either in this form or this form, it says that the normal component is continuous across the interface. So let's look at the tangential components. So for this boundary here, we're talking about tangential components. And here we are considering the case where we have some current, and the reason for that is we're going to use a loop, which is this red line here. We want that to enclose some current. And in this case here is a surface current, and use different notation, but this is the free surface current. And the reason we want this is because we're going to look at the derivation of the H equation for the boundary condition. We basically want the H along this curve here, and so we're going to be interested in looking at that. This part of the curve and this part of the curve are parallel to the boundary. And the height of this path is going to be very small in this direction, and as I said, this is delta L. So if we look at this, then we have this free surface current. We're going to take it as being perpendicular to the two H values, one below and one above. Starting with our equation for H, the line integral of H around a closed loop is equal to the free current enclosed. And as I said, the way we've taken this, the K sub F times delta L will be the free current enclosed. So coming up here then, if you look at the current along here, if we take the free current density multiplied by this length, that will give us the total current through the loop. If we then do the integral about here, then what we find is if we make these very, very small, these sides do not contribute to the line integral. We're only concerned about the line integral on the two portions here. So if we look at this, then we have what's left is the line integral around this loop will be equal to h1 tangential times delta L minus h2t delta L. And so how did that come about? Well, realize that the dl vector changes direction on top and bottom. The dot product only gives us the tangential component because dl is parallel to the interface. And because of the change in sign, we get that minus sign here. This is the left-hand side of this equation right here. So that's this side over here. We've let T be the tangential component, and so these are the components that are tangential to the interface. But then we've said that the right-hand side is equal to this. This is the free current that's enclosed by the loop. So we can set those two equal. So we have basically the equation for the H's, the tangential components, and this is the current enclosed. Delta L's on all components. We divide by delta L, and we're left with this expression for the tangential component of H. If there is no surface current, then the tangential components of H are continuous. If this is not equal to 0, then the tangential component changes. We can find the relationships for B. If we again assume linear materials, then all we have to do is define H in terms of B and mu, and so this equation right here is the same as this one where we now have our B's. So we have two expressions for the boundary conditions for H and B. Just remember that this required linearity in the system. Well, we can do the same thing as before. We can take a normal vector as we show above, the n hat to 1, and so then we can express this as a vector equation where we have the tangential components of the vectors h1 and h2, and that will be equal to the k sub f, the free current density, crossed into the unit vector n. This right-hand side gives the component of k that is normal to the loop. So if k and the loop are oriented in non-perpendicular ways, that will change the quantity of current flowing through the loop, and that's why the cross product is there. There are some other boundary conditions, and I'm not going to go through the proofs of those, and it goes back to assuming a linear material so that it allows us to take a ratio of h to m, or the other way around, to take m and put it into the h equation, and that's what I've done here. This basically is h1 tangential, this is h2 tangential, and that's equal to the free current density that we got before. You can show then that this is equal to the difference between these two vectors. That's equal to the bound surface current. And then finally we can write this in terms, it's like B, so we'll have mu1 times m over x sub m on the two sides of the interface. Finally, the vector potential has a boundary condition, and that is that the tangential component of A, remember these are vectors, the tangential components of these two vectors are equal. That's another boundary condition that might be of some use. So next time we're going to start electrodynamics. We'll start with a little bit about conduction and circuitry. I call it circuity things. We'll show you how to wire your house. We'll talk about EMF, Faraday's law, Lenz's law, and there'll be other topics in this section.